Hi, this is Mrs. LaBarbera. This is Physics Chapter 12, Sound and Light, Video 1. Today's topic is sound wave. The objectives are: know that sound waves are produced by vibration. A sound wave's frequency is the same as its source. Know that sound waves are mechanical and longitudinal. Understand speed of sound depends on particle and particle interaction. Therefore, it travels faster in denser medium. Be able to describe the characteristics of sound waves and be able to describe the phenomena of sound waves. Describing a sound wave. Sound wave is a longitudinal mechanical wave. Mechanical wave means sound cannot travel in vacuum. Longitudinal wave means the particle's motion is parallel to wave's motion. Sound wave is also referred as a pressure wave because sound creates high pressure and low pressure in the medium it travels. Take a look at this animation of the tuning fork. As the tuning fork moves, the forward motion of the tine pushes the air molecules horizontally, create a high pressure area in front of the tine and low pressure area behind the tine. Similarly, the backward motion of the tine will create low pressure in front of it and high pressure behind it. So the pressure area is moving from left to right. Therefore, it is a longitudinal wave. The pressure going from left to right, the air particles moves parallel to the direction of the motion of pressures. Now, the wavelength of the sound wave is the distance between the compressions or rarefactions. Speed of any wave depends on the property of the medium. Since the sound wave is a mechanical wave, depends on particle-particle interaction, sound wave travels faster in solid than they do in liquid, than they do in gas. So V solid is bigger than V liquid, then bigger than V gas. The speed of sound in air depends on the properties of the air, namely the temperature and the pressure. The speed of sound wave at STP is 331 meters per second. STP is standard temperature pressure. So at normal atmospheric pressure, the temperature dependence of the speed of sound wave through air is approximately by the following equation: V equals to 331 plus 0.6 times T. In this equation, T is the temperature in degrees Celsius. By using this equation, we can determine the speed of sound wave in the average temperature 20 degrees Celsius, which in average temperature, the speed of sound is 343 meters per second. So according to this, if the time delay between arrival of light wave, such as lightning, and arrival of sound wave, such as thunder, suppose they are 5 seconds, then we can determine the distance of the center of the storm. The distance equals V times T. V in this case is 343 meters per second times 5 seconds. That gives us 1,750 meters. So this distance is about a mile. So the storm is about a mile away. Frequency of sound wave is the pitch. So regardless of what a vibrating object is creating a sound wave, the particles of the medium through which the sound moves is vibrating in back and forth motion at a frequency same as its source. So the sensation of a frequency of sound is commonly referred as the pitch. So the human ear is capable of detecting sound waves with a wide range of frequencies, usually ranging from 20 Hz to 20,000 Hz. So how this is traveling in your ear. So here is outer ear, and inside the canal there is a eardrum. So this eardrum will vibrate in the same frequency as the sound wave. And this goes into this part is the middle ear. And then this transfers to the inner ear. This ear has transfers the sound wave into the electronic wave into your brain, so your brain can figure out the frequency. So any sound with a frequency below 20 hertz is called infrasound. Any sound have above 20,000 hertz is ultrasound. Usually animal can communicate with each other using sound. Velocity, frequency, and wavelength. So wave speed, again, is determined by its medium and medium only. So when sound waves are traveling in the same medium, such as all of us speaking in the same room, the wave's frequency, if the wave's frequency increases, such as somebody may have higher pitch voice, somebody have a lower pitch voice, the difference between those two is the wavelength, not the speed. So everybody's speed has the speed of their sound has to be the same. Amplitude of the sound is its intensity or loudness. So the amplitude is determined by pressure. As you can see, the top has high pressure region and high refraction region. The bottom, the difference is not that much, so it is a low amplitude sound. The amount of energy which is transferred to the medium depends on the amplitude of the wave. So the more energy it puts into plucking the string, for example, the more work has to be done to displace the string. That means the string is going to have greater amplitude, produce a louder sound. The amount of energy which is transported past a given area of the medium per unit of time is called intensity. So intensity is really the power per area. The greater the amplitude, the greater the intensity. The intensity is measured by decibel scale. So as a sound wave carries its energy through medium, the intensity of the sound decreases with increasing distance. You probably experience this as you are away from a sound, the less you can hear. Right? The mathematical relationship between intensity and the distance is the inverse squared relationship. Now, sound wave phenomenon, boundary behavior. Boundary behavior, there are three we talked about: reflection, refraction, and diffraction. Reflection of sound is also called echo. So the bat or other animals usually use sound to locate their prey, right? But in our daily experience, for example, in concert halls or movie theaters, you probably notice the walls are carpeted because in that case, we want to reduce the amount of reflection because reflection can produce noise. So we use carpet to absorb the sound rather than reflect it. Now, refraction of sound wave is most evident in situations in which sound wave passes through the medium with gradually varying properties. You probably can, I don't know if you notice it in the summer when you talk, like with your friends across the river, how sound travels. So sound travels toward cool air. So in the summer, sound travels upward. In the winter, sound travels downward. Diffraction of sound allows us to hear sound around a corner or through door openings. So you can hear people talking behind the doors because of refraction. Other sound phenomenons. The one phenomenon we have learned is interference. So we know when the two waves sound together, they produce beats. So over here, the constructive interference is a louder sound, destructive is the silence. Then you have loud silence, therefore you have beats. Doppler effect of the sound wave is observed by, we can hear the frequency change or the pitch changes. Coming toward you, you have higher pitch. When going away from you, you have a lower pitch. Resonance of a sound wave is observed. Remember, one tuning fork, vibrating tuning fork can make the other tuning fork vibrate even the other one was at rest. Another example of resonance is really playing instruments. Playing instrument is creating standing waves within the instrument to resound, to make the instrument, to make the sound louder. So one phenomenon definitely sound doesn't have is polarization. Sound wave cannot be polarized. Let's do a couple of examples. So the diagram shows a tuning fork vibrating air. The dots represent air molecules as the sound wave moves to the right, which diagram best represent the direction of the motion of the air molecules. Because sound is longitudinal wave, so the particle vibration is parallel to wave's motion. So in this case, D is the only possible answer. Another example. What occurs when sound passes from air into water? Air is less dense than water, so we know speed for the sound travels faster in denser material, so speed definitely increases. If speed increases, the wavelength has to become larger because its frequency remains the same, always the same as its source. So it's speed. The answer is number 3. Another example. A system consists of an oscillator and a speaker that emits 1000 Hz sound wave. A microwave detects a sound wave 1 meter from the speaker. The microwave is moved to a new fixed location, 0.5 meters in front of the speaker. So in this case, when you're detecting the sound, the microphone wasn't moving. It's just at one location, then at another location. So compared to the sound wave detected at 1 meter position, the sound wave detected at 0.5 meter position must have a different amplitude, because since the source is not moving, so neither its frequency nor wavelength change. The only difference is amplitude, because your distance change. The further you are away, the less you hear. So at 0.5 meters, actually you can hear better than at 1 meter position. That's the amplitude. I think that's it for today. Thanks for watching.